Okay, so this is the last section in the course. It's on eccentric impact. Okay, and I'll just describe what that means. Okay, we've seen eccentric impact in the past when we did particles. When two objects collide at an angle, then it's eccentric impact. In this case, we're looking at rigid bodies. So here's the caricature I'd like to draw. It's a rigid body, which is, in this case, say it's pinned at O. Okay, we'd only look at impact where the velocity is along the line of impact. Let me just redraw this. So in reality, well, the velocity is, let's call this B, let's call this A. So velocity of A can be in any direction. Let's call this B. And velocity of A is something like this. However, we are only trying to, so the velocity in the direction normal to the line of impact is unchanged. So we're only looking at velocity in the direction of impact. So let's call that VA1. So that's this. So if you can take VB1, if you take the velocity of B and you resolve into two components, one is going to be along the line of impact, one is perpendicular to the line of impact. So we are only concerned with the component which is along the line of impact. And then VA1 is the velocity along the line of impact for particle A. So typically we are given velocities before impact, and those are velocity of A. Well, we know velocity of A, but we'll try to take the velocity in the direction of the line of impact. So that's VA1, VB1. This is given. The unknowns are velocities after impact. And again, velocities after impact are going to be in some random direction, but the velocities normal are going to be unaffected. So we are only looking at trying to figure out the velocities of A and B after impact in the direction of a line of impact. So velocity of A to velocity of B to, okay, so two unknowns, two things are given. We need to generate two equations. We need two equations to solve for the two unknowns. So the two equations come from principles we've done before. One is conservation of angular momentum about a suitably chosen point, and that's typically the point at which you'd expect there to be an impulse moment. So in this case, I would choose the point to be O, because O is the pin joint. Yeah, tell me, question. Velocities after impact. Suitably chosen points. And then the second equation comes from the coefficient of restitution. and restitution is given to you. So velocity after the velocity of separation divided by velocity of approach. So those two principles gives you the two equations, and you can use those two equations to solve for the two unknowns which I just indicated. They are VA2 and VB2. So this is not so everything here is seen before, except that the first step, this might be slightly hard because we've not really seen how to do angular momentum about when there is a collision which is eccentric. Okay, so I'll try to solve problems based on these things. Essentially, we'll see all problems will have two equations, two unknowns, and just write the equations and solve for the unknowns.
What did it say after about? What are those last steps?
About, what should say, a suitably chosen point. Chosen point. Okay. First question. So tests of impact on the fixed crash dummy are conducted using a 300-pound ram. So that's the ram. That is released from rest at theta equals 30 degrees as shown. And allowed to fall and strike the dummy at 90 degrees, which means that this is 90 degrees. If the coefficient of restitution between the dummy and the ram is, so for the collision here, E is 0.4. Determine the angle theta at which the ram will rebound after momentarily coming to rest. So the ram is released at 30 degrees, it swings all the way to 90 degrees, hits the crash dummy, and then it will rebound back. You're going to find the angle at which it will rebound and come to rest, right, before it again hits the dummy. And the reason why it's going to rebound at an angle less than or greater than 30 degrees would be because there's coefficient of restitution. What happens is when you have an elastic impact, there's loss of energy. So if there was no loss of energy, E was 1, then it would rebound back to 30 degrees. But since that's not the case, it's going to rebound at an angle which is not 30. It's going to be between 30 and 90. So for a problem like this, there are actually multiple stages. First of all, if we have to use the coefficient of restitution equation, which basically relates the velocities before and after impact. So we know the velocity before impact. Let's call that V1. And we want to find the velocity after impact of the ram, right? That's the relation which E helps you to find, but we got to first find V1. Unless we find V1, we will not be able to find V2. And so this is a problem which involves multiple things. You got to first find velocities before impact, use coefficient of restitution to find V2, and then use V2 to find the angle at which it springs back. So this is a one problem which you got to know, not just concepts in this chapter, but some of the concepts before this. So there are three stages, right? First one is theta equals 30 degrees to theta equals 90 degrees, where our goal is to find velocity before impact. Okay, and that thing can best be done if we use, well, conservation of energy. There is no collision in going from theta equals 30 to theta equals 90. So we're looking at the instant just before impulse. So conservation of energy states that T1 plus V1 equals T2 plus V2. Again, I've used conservation of energy because the forces are only gravitational forces, and so all are conservative forces. Okay, so to use the conservation of energy, we need to fix a datum. Okay, we can choose, I would say randomly choose that as the datum. Okay, any datum would do. So the initial energy, which is at this instant 1, and this is going to be the instant 2 in this equation. So T1 is the initial kinetic energy at theta equals 30 degrees, which is clearly 0, plus the potential energy, which is basically the energy stored in the RAM because it is at a height of, what's the height? It's 10 sine 30 degrees, right? 10 is the length, 30 is the angle, and so you have to use the trick to get so it's going to be mg times 10 sine 30 degrees. So is it positive or negative? It's negative, right? Below the datum negative, above the datum positive. Okay, equals T2, which is the kinetic energy just before the ram hits the dummy, so it's half mv2 square plus, okay, let me rename this, that's not confusing. Let me call this v2 and v3 just to be consistent with my convention here, plus it's going to be the potential energy of the ram in this position, so that's going to be mg times the height or the distance from the datum to that point, so it's going to be just 10 because the length of the string is 10. Is it minus? Yes, it is minus. Perfect. Okay, so with that we can solve for, well, mass cancels off, so v2 equals g times 10, so g times 10, you get 1 minus sine of 30 degrees, then there will be a factor of 2 because of this, so it will be square root of this. So g is 32.2, put that all in there, you get 17.94 feet per second. So that's the velocity just before the ram hits the person. So the next step is impact. Okay, the ram comes with a speed of v2, it springs back with a speed of v3. We know v2 because we just computed it. We need to find v3. The way you do that is use the coefficient of restitution equation, which states that v2 velocity of, so let's call the person's velocity as vp, so velocity of the dummy vd, the velocity of the dummy before impact, let's call that vd2, divided by v3, which is the velocity of the ram minus, sorry, I got this switched. This should be velocity of separation, so it should be v3 minus velocity of the dummy after impact divided by the velocity before impact minus velocity of the dummy before impact. Vd is velocity, and then the subscripts are for before and after impact. Okay, so now we're going to make an assumption that, well, since the dummy is attached to fixed to the ground, it doesn't quite move, or it does move, but the velocity is negligible, so the velocity is essentially close to zero. So we can solve for V3, which is minus E times V2. So E is 0.4, and then V2 is 17.94, and so V3 comes out to be 7.178. So the negative sign just indicates that if velocity before impact is, in this case, to the left, then V3 is going to be to the right, which is obvious. Right? Okay, so now after impact, the velocity of the ram is 7.17, and we got to find what's the speed when, what's the angle at which it to an angle theta, which is an unknown. What's the angle at which it will again go back and come to rest? Okay, so you got to use essentially the same idea as conservation of energy, but in this case, you know the velocity at the bottommost point, you got to find the height at which the ram will go. So I would just use the same principle. Let's say that this angle is theta, the unknown angle. Put it a different angle here. Theta. So same reasoning. T3 plus V3. So this is the instant after impact equals T4 plus V4. So this is when the ram is at an angle of theta. So this is the instant 4. So the ram starts with a velocity of V3, which we found out. For the potential, we can use the same datum as before, which is the top of where the string is attached. So that's going to be mg times 10, and again with the negative sign, equals T4. So since the ram comes to rest, T4 is 0, and then V4 is going to be simply this height, which is 10 sine theta. So mg 10 sine theta with the negative sign because it's below the datum. And so in this case, mass is known, V3 is known, mg is known, theta is the unknown. So one equation, one unknown. So you can solve for theta, because you can cancel off m, and then you'll be left with essentially, it will be a simpler formula. So solve for theta, you get theta equals 66.9 degrees. So you can see that the angle at which the ram rises to is between 30 degrees, which is the original angle, and 90 degrees. It's less than, well, it's greater than 30 because E is not equal to 1. If E was 1, then V2 would be equal to V3, and it would spring back to 30 degrees. So in any collision, remember that energy is not conserved. So one mistake I normally see in exams is people try to use conservation of energy during impact. And impact energy is not conserved. And that's obvious. If you look at half mv2 square, that's the kinetic energy of the ram. It's not the same as half mv3 square. V3 is less than V2. Okay, questions? Questions? Okay, here is next problem. Okay, the mass center of the 3-pound ball has a velocity of 6 feet per second as shown here. When it strikes the end of the smooth 5-pound slender bar which is at rest, determine the angular velocity of the bar about the z-axis just after impact if E is 0.8. So the bar is stationary, the ball impacts point B with a speed of 6 feet per second. You got to find the angular velocity of the bar after impact. Okay, and since you're given E equals 0.8, what it means is that the ball hits the bar and rebounds. Okay, if E was 0, then it would be a sticking collision, plastic collision. If E is anywhere between 0 and 1, it means it will rebound. Okay, so if the ball is going to rebound,
if it were to stick, we can like take it, give it on its mass to the rod.
yeah, there is mass on the rod. Yeah, it's about here.
Okay.
Yeah, this is no friction, so it's actually a pin here, which allows it to rotate without there being any friction. So that's 5 lb. Okay, so if the ball rebounds, so then we'll have a velocity of the ball after impact, which is clearly an unknown, and then the angular speed of the bar after impact. So that's an unknown, that's an unknown. There are two unknowns. So this is where this falls under that. In my notes I said you'll have a problem with two unknowns. This is exactly the case. You have two unknowns, so we got to generate two equations to solve for the two unknowns. So we need two equations. Before we write the equations, let's draw a free body diagram during impulse. Okay, so this is, so maybe the right word is FBD. At the time the ball hits the rod. Okay, so it's when the ball hits the rod, and I'm going to draw a free body diagram of the ball in contact with the rod. So when you draw a free body diagram during the point of collision, okay, though there are forces between the ball and the rod, but because I drew one free body diagram for both of them, those impulse forces at collision are internal to the system, so they will not appear in the equation. They will not appear in the free body diagram. However, if you had drawn separate free body diagrams for the rod and for the ball, yes, there would be impulse forces because of the collision. So in this case, because of the impulse, there would be an impulse on the rod. Impulse. So if there's an impulse and you do not care about the impulse, you do not want to compute that, then the best way to get rid of the impulse in the equations is to do angular momentum conservation of angular momentum at O. So when you do conservation of angular momentum at O, the force of impulse will not show up in the equations because the moment arm is effectively zero. So we actually do conservation about this axis. So H about axis Z, if you like, before collision equals H about the Z axis after collision. 1 to before and after collision. Okay, so we need to find HZ1 and HZ2. Uh, in the case, so h is what? It's the angular momentum. H is either r cross mv, that's for a particle, or h equals I omega, that's for a rigid body. So this is particle, rigid. Okay. For a particle, h is r cross mv, and for a rigid body, h equals I omega. Okay, this is not new. This is something which we've done in the past. For particle, you got to go back to your notes to, I think, chapter 15. You see the equations for particle, and rigid body, something we did in this very chapter. Okay, so before impact, only the ball has angular momentum because its velocity is non-zero. So its angular momentum is its mass of the ball, velocity of the ball, times the distance from the axis to the point where the ball collides. So that's going to be, I believe, 2 feet. Okay, I just wrote it down as MVB2, but it's really, you got to do the cross product. Okay, so to get the cross product, it's R cross MV, so R cross V. So the vector R is this way, the vector V is this way, R and V. So if I got to do the cross product, I need to curl my fingers from, maybe we redraw this, R V, okay, I switched it, V, that's direction of V, this is R goes from the center to B. So if I do V cross R, sorry, R cross V, R cross V, so R cross V, I need to curl my fingers from R to V. My thumb gives the direction of the angular moment H. So that says that the direction is going to be negative V. So I need to put a negative sign here. Equals the angular momentum after impact. So after impact, the bar would have a speed, and so would the ball have speed. So for the bar, if you assume that, well, we can assume either way. So I had shown that in the clockwise direction. So let me just choose it in the counterclockwise direction because the convention is counterclockwise positive. So if I curl my fingers along omega, then my thumb gives the direction of the speed, which is upwards. So the angular momentum due to the bar is going to be inertia of the bar times omega of the bar. Okay, and that's positive because my convention is, I'm just going to assume omega is positive counterclockwise, and if that's the wrong direction, then the math will tell me it's the wrong direction. Okay, so that's due to the bar. I also need to account for the angular momentum due to the ball because the ball is going to rebound. So I have an option now. I can either choose the velocity of the ball to be that way, as I've shown there, or I can choose the velocity to be to the right. Oh, sorry, coming towards you. Okay, if I choose the velocity, so no matter which direction I choose the velocity to be, I need to take the cross product because I have to eventually do R cross mv. So if you assume that velocity is this way, like I've shown in the direction in the diagram here, so velocity after collision, let's call that vb. The vector r is still this way, so I need to do R cross mv. So I curl my fingers from R to VB. So when I curl my fingers from R to VB, my thumb gives the direction of the angular momentum again, R to VB. So go from R to, my thumb is in the upward direction, which means that the magnitude is positive. So I'll have R VB times n. I'm using the same notation here. Let me call this simply V. The first one, let me call that V because I'm using VB for after impact. So that's it. So this equation by itself has two unknowns. Omega is an unknown, VB is an unknown. The velocity is given, it's 6. MB is known. Inertia for rod about axis passing through about its center, and that'll be given to its 1/12 m of rod L square. Okay, so I is known because the mass of rod is known, length is 4, MB is known, R is known, and so you cannot solve for both the unknowns because you have a single equation and two unknowns. Those are the unknowns. So we need to generate the second equation, which comes from the coefficient of restitution, the E equation. So E minus E equals velocity of separation, velocity of separation divided by velocity of approach. So velocity of separation is going to be all the velocities after impact. So it's going to be velocity of G or velocity of B, is what I called it, this one, minus it's going to be the velocity of this point, right? When there are two particles colliding, it's going to be the velocity of the points of interest. So velocity of capital B divided by the velocities before the collision. So velocities before collision is velocity of the ball before collision is 6. The velocity of point B before collision is 0. Before collision. Okay. Now the thing is, I cannot use this equation by itself to solve because VB is unknown, E is known. I don't have a means, well, VB is not in my first equation. So somehow if I can tie VB with the angular speed, then I can solve for both the unknowns. What I do is I actually can write an expression for VB as a function of omega. And this comes from your kinematics. If the velocity of this point is 0, then the velocity of point B is going to be, so VB minus velocity of B is going to be omega times the radius, so 2 divided by 6 minus 0. So that's the relation between VB and angular speed. So now I have, well, two equations and two unknowns. Let me circle this, so much going on here. That's my equation 1. And this is equation 2. Okay, I don't have space. Let me write the answer. The velocity after impact, which is VB. So two equations, two unknowns. You can solve for the two unknowns. Velocity of B is 2.143 feet per second, and velocity, angular velocity omega is minus 3.47 radians per second. The negative sign indicates that my assumed direction for omega was incorrect. It was not, shouldn't be clockwise, counterclockwise, it should be clockwise, which makes sense. This is going to rotate clockwise or this way. So my thumb is going to give the direction of speed. Okay, is that clear? Any questions? Questions?